Okay, now we continue with Saad Khan from ETS, please.
Okay, thank you very much, Javier. First of all, I'd like to say in the program it just says my name, Saad Khan. It's probably because there are so many different contributors to this paper, including colleagues from UND. I'll be talking about the MAP, which is a multimodal assessments platform for interactive communication competencies that we've been building at ETS. And here's a brief outline of what's to come. I'll give a brief introduction, the motivations behind this work, some of the key challenges that we're trying to address with specific innovations in evidence extraction. I'll talk about the MAP itself, the use cases that it's driven by. I'll give you, starting with a brief overview of the solution, the key capabilities, and the features, and I'll dive a little bit into the technical approach detail. I'll conclude with a demo and discussion on potential other use cases and some concluding remarks. So let's start. Well, there's growing realization that to be successful at the college level and perhaps even beyond that into the workplaces, one needs competencies and skills above and beyond reading and writing and mathematics. Of course, I'm talking about the so-called 21st century competencies, things like communication ability, collaborative problem solving, team interaction, and so forth. And these are skills and competencies not just for students, but potentially for professionals as well, for example, teachers in a classroom. Unfortunately, assessing these competencies is pretty complicated, and traditional psychometric machinery is not particularly well suited for some of these measurements, in part because these require an assessment of not just the final outcome, but also the steps and processes that were used to arrive at a particular conclusion. For example, how did people actually collaborate? There's also a pretty complicated interplay between cognitive and non-cognitive behaviors in these competencies, for example, motivation, self-control, and emotional regulation. In fact, a number of keynote speakers have already spoken, and I think Signe will be talking about more of that later in the conference. So the challenges really are, how do we build tools that can assist humans in making assessments or measurements of these competencies in real-life authentic scenarios, in vivo, as in if you're talking about assessing somebody's collaboration skill, why don't you give them a problem to solve collaboratively and try and assess their competency over there? Can we do this objectively, reliably, and scalably? Now, somewhat paradoxically, it's not that we don't have enough data. In fact, there is a data deluge. There's a lot of data that's captured in a number of different modalities. However, it's highly unstructured, it's very noisy. And the real challenge is extracting meaningful evidence, which is indicative of the final competency, and making meaningful inferences from that, from the very unstructured and noisy data. The innovations that we've been bringing and working on to address these challenges are multimodal analytics, where we're trying to capture behavioral data holistically through a number of different sensors, as well as building hierarchical inference models, which are in part inspired by biological processing systems, aka the brain, trying to build intermediate representations to connect or really solve that problem of bridging low-level data capture and the high-level competencies that we need to be able to measure. Of course, multimodal analytics is above and beyond simply capturing data holistically from a multitude of sensory modalities. We're talking about building computational models for automated measurement of behavioral attributes the way a human expert would. For instance, if I'm observing a teacher teach in a classroom, I will bring to bear my knowledge based on what I see with my eyes, what I hear with my ears, and so forth. So, for instance, in this picture, can we make some judgments about the teacher being engaged with the students based on the voice, facial expressions, body posture, and so forth? With hierarchical inference models, in a nutshell, we're trying to address the big challenge of how do we bridge inferences the capability to make inferences on very high-level competencies, for instance, interactive communication ability, from the data that's actually captured in the form of video, 3D, and audio spectrums. And the key over here is to be able to build intermediate representations where each layer is essentially abstracting out a lot of the noise from the layer below it. So going from the multimodal data, can we get to low-level features, for instance, facial expressions, gestures, speech prosody, and so forth, which in turn could be used to make inferences on overall affect, fluency, vocabulary, and ultimately lead to the evidence that could be used in a model to assess interactive communication ability. Now notice over here there are two arrows. It's not purely data-driven bottom-up. In fact, we're trying to use as much as possible from theoretical models to be able to really guide the data analytics, as in what would be the sub-skills associated with the top-level competency and so forth, which we ought to be able to build models and detectors to classify. So it's a very iterative bottom-up and top-down model. To really take the message home, I'll give you an illustrative example around potentially assessing teacher competency in a classroom. Now, Doug Lemov, in his excellent work, Teach Like a Champion, talks about several dozen behavioral attributes of good pedagogy. And these are all observable behaviors. So for instance, over here what you see is a teacher who's taking a spot in the classroom that's called hot spotting. She's just basically making sure that she's standing in a position in the classroom where she can make eye contact with as many students as possible. It's a very simple behavior. But there are many others that I'll talk about as I play this video, and you'll be able to really notice that too.
As I walked around, many of you were able to tell me what the difference in opinion is between Alexandra and Atticus on Calpurnia. So our discussion is going to focus on why.
So a teacher asks a question, but instead of letting the first student who raises her hand to answer, she's going to wait. So that's 1 second, perhaps one hand, 2 seconds, 4 hands, more and more hands. This simple skill is called wait time. All it's doing is that it's giving some of the students who need more time to be able to really comprehend the question to get engaged. Once again, she's going to ask a question, and this time actually she waits almost 10 seconds.
The question is what's agitating him. Thoughts? Great, and if you're looking at your book, make sure you pause and track our check.
So nearly the entire class raised their hands. There were other attributes over here too. If you notice, she was walking down the hallway, making sure that she's minimizing distance from the students in different parts of the classroom, making sure that all come into the fold over here. So why this is interesting to me is because these are all observable, tangible attributes of good pedagogy. And in a way, they're content agnostic. This is not to say that the content itself or what the lecture was about is not important. Of course it is. But this is a complementary channel of communication that good pedagogy is about, that we can try and actually measure tangibly with multimodal analytics. Of course, we've been bringing to bear these ideas to build a platform that we call MAP to assess interactive English language communication above and beyond what perhaps one could do with TOEFL. The potential users over here are university admission offices, which are in the need of better tools to evaluate English skills, and perhaps even English language learners who need formative feedback to improve their dialogic, interactive English speaking ability. Just briefly, before I go into some of the details, we start off by capturing audiovisual. There's an audiovisual Skype-like interface where we can capture holistically the data about the candidate, having an interactive dialogue either with a real person or a virtual avatar. The data from this conversation is then analyzed with multimodal analytics using a number of different algorithms, including ASR, speech and acoustic feature analysis, facial feature tracking, action units, head gaze and eye gaze orientation detection, facial expressions, affect, and gestures, and so forth. These features are then distilled to provide feedback on security biometrics, I'll get to that. Behavioral engagement, affective engagement, I'll describe those, the distinction over there. Speech delivery and language use scores. But let's work our way backwards, starting with the speech. The system provides feedback on two dimensions of speech, delivery and language use. With delivery, we're talking about capturing speech fluency and pronunciation. And with language use, we're talking about grammar and vocabulary. Now, in any particular non-native speakers, these skills might be highly correlated, but they're really learned and evaluated in different fashions. The models, the subscore models that we built for these are produced by linear regression, which was trained on approximately 541 spoken responses that were human-coded. Of course, the low-level features that we extract from the data, in the case of delivery, we're talking about 11 features from number of words, number of lexical types per second, mean deviations, and statistics of that, including some pronunciation features too. For instance, the sum of word level and phoneme level acoustic model likelihoods. With language use, similarly, we're talking about a number of different low-level features. For instance, number of distinct lexical types, number of lexical types per second, and so forth. The MAP system also gives feedback, and it's got detectors on based on machine learning-based detectors on behavioral engagement and affective engagement. These are trained on open source data sets, particularly the CMAIN data set. Some of you who've worked in the multimodal space are probably familiar with that. It consists of 95 dyadic conversational interactions between users of this nature. If I can just play that.
And what character would you like to speak?
Spike.
Hi, I'm Spike. I've got a bit of a temper. The world makes me angry. I don't really like the world. I don't really like people I know. Full of fools. What makes you angry?
People who judge you for no reason.
Right, that gives you the basic idea. The data is fully annotated along a number of different dimensions, including valence, arousal, and basic emotional states. With behavioral engagement, we're trying to capture on-task behavior. So for instance, as you can see in these two illustrative examples over here, and we use a Visage SDK-based detector of face and head orientation and use a scanning time window approach where student state is marked as behaviorally disengaged if there's a failure to register face, as in the face is completely not even in the field of view or mostly obscured. Or you have a head orientation, which is a particular delta outside of the facing directly into the screen, which is of course configurable. Now, that is indicating whether you're completely disengaged, not even looking and distracted. With affective engagement, we're trying to capture the notion of being in a state where you're in a heightened state of arousal, so you're not really bored, and you're also projecting positive emotion or positive valence. So if you look at the scatter plot of the arousal and valence distribution of the annotation from the CMAIN data set that I described just a moment back, this is, it's all over the map. Of course, it makes sort of sense. We're talking about the x-axis over here being valence, negative valence meaning negative emotion, positive emotion. Arousal being positive, you're really animated and energetic, versus negative arousal being rather passive. So what we're trying to capture is this quadrant over here, where you're in a positive state of arousal and a positive valence state. And that's really our training data that we built our model for affective engagement. The features that we use include head pose, head orientation, eye gaze, and a number of different facial action units on 12-second scanning windows. We experimented with a number of different models, including logistic regressions, SVMs, and multi-layer perceptron classifiers, and found that logistic regression actually did the best over here, giving us an area under curve for the ROC curve about 0.67. So you talk about 64% accuracy over here. And not great, but certainly giving us meaningful data. The final feature, the capability in MAP, is security biometrics. This is in part driven by the desire to really deter cheating. So in this case, we have the potential to capture a second level of data of the particular candidate. So for instance, the candidate showed up at when they did their first test in the form of the TOEFL, and now you've got a second level of data available for the purpose of verification. Was it the same individual who showed up at the test site, or was it a proxy? We hope that having buttressed our security biometrics, we will also add to the validity and integrity of the score. The biometrics engines that we built are based on deep learning architectures, both on the speaker identification based on speech and face recognition. In the interest of time, I'll just talk a little bit about the face recognition piece, where we have obtained state-of-the-art accuracy scores. Just to illustrate the complexity of the problem, the data capture conditions can vary significantly between the two instances of data capture. So we're talking about variation in lighting conditions. People's facial expressions might be changing. You might have different garments, glasses, no glasses, shadowed, or perhaps even very blurry images. So these are the kinds of capture conditions we don't necessarily have full control over, and the approach that we built is really trying to address these kinds of technical data capture conditions. In a nutshell, the approach is based on a deep learning architecture, in particular convolutional neural networks, CNNs. It starts off by doing face detection between the two images that we want to be able to verify if it's the same ID. The face detections are used to then you do a 2D or a 3D based facial feature alignment. So we do much more fine-grained feature detection around the face, and then register the two of them, so we're talking about the same pixel location in one image corresponding to a similar location in the other. So if you're extracting features from around, say, the eyebrows on one image, we're doing the same thing in the second image. The CNN over here, so basically we're building, it consists of a number of different convolutional and then pooling layers. In essence, the output of the CNN process, it's really being used as a feature embedding approach. So you take in the entire pixel patch of the face, and the output is a 4096 dimensional feature vector, sort of a signature of that particular image patch. Once you have the two signatures between the two images, you can do a comparison between them. Basically, it's essentially L1 norm. Now, we've tested our approach on a number of different data sets, and we conducted a benchmark study where we evaluated the performance of our approach vis-a-vis commercially available products. And this chart over here, which is showing you the missed probability versus the false alarm rate of our approach, I'll probably highlight a couple of curves over here. The purple one is our face recognition curve over here. And to compare it, you got to look at the blue one, which is a commercial solution. So certainly our approach is much better than that. And the second one I will point out to is the green one. That's the result from the fusion when we fuse the face recognition with the speaker identification from the speech data. So, and to compare it with the commercial option, that's the black curve over there. The equal error rate that we got for our fusion approach is 0.67, so which is remarkably good. All right, so I'm about to conclude in a few slides. I'll give you a quick demo of what we have built thus far.
And I work for the Educational Testing Service. How are you doing today?
Hello, Mr. Perry. Very nice to meet you.
I guess you are wondering why I called you. This video conversation is to be a follow-up from the TOEFL test you recently took.
Oh, okay. Just me? What do you want to talk. Is there something wrong?
Oh no, there's absolutely nothing wrong. The purpose of this meeting is to better estimate your English language speaking and communication abilities. I will be asking you a few questions about yourself, your background, and your goals. Are you ready?
Oh yes, Mrs. Henry. Okay, what do you want to know?
Okay, first question. When did you first start taking classes in English?
Oh, I started English lessons in middle school. So, let's see. I was about 10 years old.
Okay, and how many classes or hours a week did you spend on learning English?
In middle school, we started with one class a week, and that was 2 hours. And then, this was, what's the word? Increase. Yes, increase. So, by high school, we had English 5 days a week, 1 hour in length.
Excellent. And did you have opportunities to practice your English skills outside of school?
Not everyone in school like it, but I really like learning English.
Okay, now tell me about your academic plans.
I am majored in business administration and well to get a master's degree from American University. And my parents think it is a good idea for me to study in the USA.
That sounds like a smart idea. There are a number of quality MBA programs offered by universities in the USA.
Yeah, I think it is a good move too. I have applied to 5 schools, but I do need to get a good score on the TOEFL exam.
Yes, and having good English communication skills should help you obtain an excellent education in the US.
Great, that's exactly what I want. Anything else, Mrs. Henry?
No, I think that just about covers it. So thank you so much for talking with me, and good luck in your future endeavors. Goodbye, Yuli.
Okay, goodbye.
Then we'll go into the various different tabs over here. I should have mentioned that this was an illustrative example. This is not an actual candidate. These were actors. The running dashboard over there were the various low-level features that we're picking up, not necessarily something that would be part of a report, but that's illustrating the capability of the system. But I feel there are potentially many other use cases for capabilities of such nature. We can perhaps even get to a point where we can try and assess behavioral attributes of job candidates along a number of different behavioral dimensions like communication, engagement, conscientiousness, and so forth. In fact, there is some ongoing recent work along those lines outside of ETS. We've also been looking into building better tools to be able to measure and assess CPS, collaborative problem-solving skills, using multimodal analytics and building the same hierarchical inference models. So in conclusion, I'd like to say that I feel multimodal behavioral analytics is a key enabling technology for the next generation of in vivo assessments and learning tools. For instance, interactive communication ability, CPS, and non-cognitive and soft skills in general. We're very excited about new developments in machine learning, particularly deep learning architectures and analysis of time series process data. We have done some very baby steps over here in building prototypes, but it's really important that we scale things up with validity studies and really make sure that the kinds of evidences and skills that we're picking up would be validated for the kinds of inferences that we want to make about the competency. And that's where we can certainly leverage cloud computing devices and large-scale testing and development studies. So with that, thank you very much.
Thank you. We have 5 minutes for questions.
Yes.
So, did you look at cross-reference these data sets with the assessments, the grades of the students?
The assessments that what?
The grades, the performance of the students?
That's a great question. We haven't actually done that study yet. We're working with various different universities to be able to get that kind of data and make some validated inferences on that to see if actually there is a connection between grades in school, for instance. This is in part my conjecture and my gut feeling that I think these skills, and of course, it's not just me. The whole community is very excited about these 21st century competencies, how it might be valuable and might have transferability to a variety of different use cases and of course, ultimately to educational outcomes. But in this particular study, we haven't gotten to that point, but we hope to certainly. Yes?
In your convolutional neural networks, how many hidden layers did you use and how many hidden neurons did you use in each layer?
So we had 7 layers. I'm not exactly sure how many neurons in each layer. Of course, that sort of depends on how we're doing the max pooling over there. The first layer would be basically the same number of pixels, which would be, we downsample each, when we start the image after the registration, to 100 pixel by 100 pixel. So I'm talking about, 10,000 neurons at that particular layer. But that's just for one convolution. The number of different kernels that we've got, that just multiplies into that. I'll have to actually get back to you. It's a specific number of neurons that we had in each layer on that. Yes.
Hi, thank you for that. Could you speak a little bit about the ASR? I'd be very interested in knowing it's actually, especially for second language speakers, and maybe a little bit about the algorithms that underlie your syntactics and grammatical.
So the ASR that we use is an in-house ASR that we built on an open source toolkit called Caldi, which is also based on it has a deep learning architecture in there. Now, the low-level features that we're talking about over here are MFCC, melt frequency substance, sort of phonetic features over here. Now, of course, the data is, the data that we have actually used to build it is for non-native speakers itself. So we've tried to contextualize an existing, say, a background model from native speakers onto the non-native speakers. I don't know over the top of my head exactly the precision and the accuracy on that. Of course, we do transcription of the logs and then evaluate the accuracy on that metric. But yeah, thank you.
So my next startup is going to be training candidates how to play this game with the artificial interviewing engine. So that is inevitable, in fact, if these technologies do take off. And so that'll be an interesting sort of Cold War where you have to figure out whether somebody's overacting in order to fool the AI.
That, in a way, is the holy grail of AI. We're talking about potentially building something that solves the Turing problem, Turing machine problem. Yeah, I think that's certainly a possibility, people gaming the system. My hope is that the system ultimately is strong enough that if you're gaming the system, you are acquiring the skills that are really needed to succeed ultimately.
And if I can just add, actually, I think that's a really interesting strategy for learning analytics in general. Smart students will always try and game the system, so can we design it so that by doing that, you've actually accomplished the learning intention?
Exactly.
I have seen literature that uses image recognition techniques to detect fake smiles.
Sure.
And they do it by looking at the reactions around the eyes.
Could you speak to how domain-specific the AI might be, or how it could maybe detect discipline differences in effective communication?
Certainly. We're trying to of course, the models that are built over here will essentially be reflective of the training data that's used to build the models. In a way, my view on this problem is to have detectors of lower mid-level features which are built on data that is representative of a variety of different contexts. However, we can have another layer, an inference layer on top of that, that could be contextualized to say, how do you actually use the behaviors that are being detected in one context and piece them together to get to a score of or a measurement of a competency which is more customized to, say, interactive speaking ability in the case of making a presentation versus speaking ability when you're a teaching assistant in a classroom. So that's a higher level layer of inferencing that could very well be contextual. Maybe you could use something like a Bayesian network over there to be able to really correlate the low-level data, which as I said earlier, ought to be agnostic to the particular context.